The power rule is something that's also sometimes known as integration by substitution, and it's the first real technique we have for doing integrals. So we talk about techniques for integrals rather than really rules because there aren't really any universal rules. There's just different moves we can use when we notice that the integrand is of a certain form. So this requires a little bit of setup. So that's our regular powers of x formula. That's really the one formula we have so far. The integral of x to the n is x to the n plus 1 over n plus 1. Now we want to extend that to being like a function to a power. So let's say if it was x squared plus 2 to the 10th or something. How can we use the power rule on that? So it requires a little bit of setup, and it involves that dx. So that little dx that we haven't really used is called the differential, and now I have to define that. So rather than the f prime notation, kind of switch over to thinking of what we call Leibniz notation, which is that dy dx. So when you see dy dx, you just think, okay, the derivative of y with respect to x. That's what it means. So if y is a function of x, then another way to write f prime is dy dx. But it looks like a fraction, and there actually is a reason for that. So here is the reason. Now we're going to actually treat it as a fraction. Okay, so definition. Right, so y is a function of x, f prime of x and dy dx are the same thing. Then what we call the dx is called the differential of x. You can think about it as having a quantity. You can think about it as just having quantity equal to 1, because like the derivative of x is just 1. And then the derivative of the thing on the bottom, dy, is the differential of y. And if you do think about that as a fraction and you move the dx to the other side there, then you have dy equals f prime of x dx. So you can think about that as f prime of x times dx. But again, dx doesn't really have any quantity. You can think about it as the quantity as just being 1. So this is all a way to move stuff around in that integral, to rewrite it in terms of like a new variable, so we can use our rules on more complicated stuff. So when you see dy dx, like one of the reasons it looks like a fraction is because remember, a derivative is like the slope of a curve, and the definition of slope in the first place was a change in y over change in x, right? Rise over run. Or think about a derivative as a rate of change. The derivative of a rate of change is like miles per hour, right? Miles over hours. So it really is like dy over dx. Okay, so there's just an example. If I give you y as this function, 3x squared plus 4x, then dy isn't exactly the same as f prime, but it pretty much is. It's just 6x plus 4 times dx, and you do want those parentheses there because there's more than one term. So really for now, just think, okay, the differential is like a derivative, but instead of saying dy dx equals 6x plus 4, we're saying dy equals 6x plus 4 times dx. Okay, so it's just a rearrangement of that. And hopefully this isn't as complicated as it seems, and it's going to make sense soon why we're defining this stuff. Okay, now we got to do a little backwards derivative thinking. If you have a function that's like a function to the n, we're using u of x. That's just what we use for something called the substitution. So I'll show you an example, but if you have a function to a power, the derivative of that by the chain rule is, okay, first you deal with the power. So the power comes down and then gets reduced by exactly 1. And then by the chain rule, you multiply by the derivative of the inner function. You know that. Example, if y is 2x cubed plus 3x squared, all that to the fifth. Now, you know that you can multiply that out 5 times, but it'd be a huge pain, so it's better to use the chain rule, so you know how to do that derivative. So dy dx, right, the power comes down, 5 times 2x cubed plus 3x squared to the fourth, times the derivative of the inner function, which is, right, 6x squared plus 6x. So, therefore, since the derivative of that thing is that thing, the integral of the second thing is the first thing. So we just want a way to do that in general. If we see an integral that looks like that, If we see an integral that looked like 5 times blah blah to the fourth times its derivative, we would say, oh, we can kind of undo the chain rule and put that thing back together again. So there's a general way that we do that. All right, so that's what I just said, only generally. So if you have the integral of a function to a power times the derivative of that inner function, then you can integrate it just like you would just using our power rule for integration. The power goes up by 1, and then you divide by that same number. So it's that function u of x to the n plus 1, and then dividing by n plus 1. All of these are nice because you can, once you get to the end, you can just do the derivative of what you got, and you should get the original integrand. So they're all checkable by just doing a derivative. So just think about that thing on the right-hand side, taking its derivative. The n plus 1s would cancel out. It would go down to just an n, and then by the chain rule, you'd have to multiply by u prime, and look at that. That's exactly what we see on the left-hand side. Okay, back to our kind of differential notation, u prime of x dx. So that thing in the previous slide, u prime of x dx, is the same thing as just du, right? So u is a function of x, so the differential of u du is u prime of x dx. So that all can get replaced, and it gets much simpler. So if du is the derivative of u times dx, then that whole thing on the end there just becomes du. So now it's really exactly the same thing as the power rule, except u isn't just a variable, u is a function. So that du thing involves u's derivative. So it's only a very specific type of integral that we can even do this way. And that's okay, because we're going to focus on the specific types that we can actually do, because you can't just do any old integral like you can with a derivative. So what this is called is making a substitution. You've maybe seen it before in mathematics. If you have something that's too hard to deal with on its own, you just make up a new variable, basically. You say, okay, let u equal x cubed or something. And then you deal with that. Maybe you use the quadratic formula on it or something, and then you switch it back. So the way your book describes it and the way it is in the homework is a little different than the way I do it. So it's just the process is a little different. You're actually doing the same exact stuff. I'm not like diverging from the book. There's only really, one way to do this, that this works. Okay, so look at that integrand. I mean, it looks gnarly, but it's just, okay, 8x to the fourth plus 3x cubed to the eighth times 32x cubed plus 9x squared. So the key to this working, the only reason this would ever work is if you look at that second term, that's the derivative of that inner function of 8x to the fourth plus 3x cubed. So that's all you have to look for. One of these things is the derivative of one of these other things. So the thing that becomes your u is always the inner thing. It's always some function that has something else being done to it. So this doesn't just work with the power rule, but that's all we got for now. Right, so that 8x to the fourth plus 3x cubed is being exponentiated. So that's having something done to it. So that's like the inner function. That's going to be our u. And then our n is going to be 8, the power of 8. And then that whole thing on the end, 32x cubed plus 9x squared dx, is just du. So the point of this is to transform this pretty complicated looking integral into a much simpler one by making a change of variables. So we're just going to make up a new variable u, right? That's the cool thing about math. You can just make stuff up and nothing explodes. So we're going to say let u equal 8x to the fourth plus 3x cubed. Right, so again, that's the thing you have to pick up on. In the future, I might just give you a bunch of integrals and say, do this. I'm not telling you how. So the key to it being like a u substitution integral like this is that. If you don't have this, then this won't work. Right, so the whole thing just becomes u to a power du. Right, the whole thing on the end just becomes your du. So you see what I mean? Now it's quite simple. Now we just use the power rule. Oh, that's just u to the 9th over 9. And then, so the thing is, at the end, you can make up variables, right? That's fine, but it's still just something you made up. So you have to put it back in terms of x, right? This isn't the answer. I didn't ask about u, I asked about x. This is just a means to an end, to getting to to a function whose derivative is this original function. So that's easy. Just stick back in whatever u was in the first place. Right, that's the answer. 8x to the 4th plus 3x cubed to the 9th over 9 plus c. So at this point, I would really encourage you to check this by differentiating. I'm not going to do it because derivatives are easy at this point. But doing that not only lets you see like, oh, my answer is actually right, but you kind of get why we do it this way and how this is. It's not a reverse chain rule. It's a way of kind of undoing the effects of the chain rule. So you can maybe kind of do that derivative in your head. Okay, the 9 comes down, cancels that 9, drops down to an 8, and then we would have to multiply by the derivative of the inner function, which gives us that 32x cubed plus 9x squared. Boom, that's it, right? So you can almost kind of look at it and figure it out. And then with this technique, with the substitution, you'll almost be able to skip the u at some point. Once you do this enough, you'll see that, oh, you can probably just jump right from there to it's u to the 9th over 9. For now, obviously, bear with me, because this is a very important technique in math, is making a change of variables. Another one, so integral of x squared times the square root of x cubed minus 4. So when you see something like this, never think like product rule. Like, oh, do I use some sort of a product rule for integrals? There is no such thing. There's absolutely no such thing. And there's no such thing as a quotient rule for integrals. So now there's something called integration by parts that sort of reverses the effects of the product rule, but we're not there yet. But never think like there's just some rule that, okay, if it's a function times a function, the integral is this. Again, the only reason this works, and hopefully you've figured this out by now, is that if you look at the inner function, the only function in there that's really inner is x cubed minus 4. What's the derivative of x cubed minus 4? It's actually 3x squared. Hold on, we don't have 3x squared, we just have x squared. But that sure is easy to fix. It's pretty easy to get rid of a 3. You just divide it out. So again, eventually you'll be able to do this without going through the whole process and say, okay, I just need to like have a 1/3 in my answer to deal with that problem. But for now, watch my steps. And again, this is a little different than the way your book explains it. That's not wrong. If you like your books way better, use the book way. This is just my, I guess, more old school way. Okay, so again, that's the only reason this works, is because if u is that thing in there, so you don't really have a choice for what u is, it's inside of something else, then du gives you 3x squared dx. Now, what do we got in our integral? We have x squared dx, right? We don't have a 3. But how would you rearrange that? Just think of that thing du equals 3x squared dx as an equation. It is. And just think, okay, if I just move that 3 to the other side, I have exactly what I want. I have x squared dx, that gives us the entire rest of the integral, equals 1/3 du. So I'm just going to have a 1/3 in my thing that I integrate. So it's all about identifying what you want. You want x squared dx. If it helps you, rewrite the original integral with the x squared on the end. So you basically solve the equation for x squared dx, which is that. That's it. You're done with that part. So now I think I will rewrite the original thing. So now I need everything in that original integral in terms of u. That's the thing. That's why we have to deal with the differential, the dx, because we need everything, including that, to be in terms of our new variable, so we can just use the simple power rules that we already know about. All right, so see what I'm saying? I rearranged the original integrand. So now it's the same thing. I just put that over there. So the square root of x cubed minus 4 just becomes square root of u. And the x squared dx becomes 1/3 du. Now our integral is simple. The 1/3, obviously, we know from our constant rule, just comes outside. You're going to eventually want to do that like in this step. You can essentially skip this step and just jump there. You know that. You know that constants come outside. Okay, so now again, you're just using the power rule. So you know how to do the integral of a square root. You're probably going to want to rewrite it as u to the 1/2. I didn't, but we've already done this one. So the integral of u to the 1/2 is just u to the 3/2 over 3/2. right? The 1/2 plus 1 is 3/2. So obviously we want to clean that up a little bit. First we have a compound fraction. Nobody likes that. So you just flip it and multiply. So that's what, 2/9. So finally, the simplest version is 2/9 times u to the 3/2 plus c. And then again, right, don't leave it like that. U is just a kind of a dummy variable that got us here. So just pop x cubed minus 4 back in. Beautiful. Okay, that's it. Again, check by differentiating. You can almost work through it in your head. Okay, the derivative of that, so the 3/2 comes outside. So let's see, 2/9 times 3/2 is 1/3. And then the 3/2 drops down to a 1/2, so that's the exponent now. And then you would multiply by the derivative of what's inside, which is 3x squared. What do you know? That 1/3 from the beginning gets rid of that 3, and then you just have x squared times x cubed minus 4 to the 1/2, which, boom, that's what we were looking for. So I would encourage you to do that. At least at first, you can always check these answers by finding the derivative of your result. One more, I mean, this looks nasty, but it's really the same as what we've been doing. The only function that you could really describe as inner is that x to the 6th minus x to the 4th. So not only is it being raised to the 3rd power, it's actually also like inside a denominator. So you could rewrite this and think of it as just being raised to the negative 3rd power. Okay, so that has to be our choice. So then you look at it and say, okay, what's the derivative of that? The derivative of x squared minus x to the 4th is 6x to the 5th minus 4x cubed, right? Now that's not exactly what we have on top there, but it's only off of it by a constant multiple, and that's the kicker. If it's off by a constant multiple, we can do the kind of move we did last time, where we just move the constant around, and this technique will still work. We'll just have like a 1/2 or something in our final result. Right, okay, so generally this shouldn't be vague. You have no choice. U is the inner function. That's the only inner function here. Down the road, we might get some stuff where it's a little more like it might be misleading as far as how to do it. But for now, it should be obvious. All right, so there's your du. Now notice, okay, that doesn't quite look like the thing I have in my numerator, but if I factor a 2 out of it, it will. Right, and that has to be that way. If this were 6 to the x to the 5th minus 3x cubed, this wouldn't work. There probably wouldn't be an integral. It might be impossible to do or extremely difficult. So see what I'm saying? It's a very specific form of function that this even works for. All right, so factor a 2 out to make it look like the top. So it takes it's a little bit of cleverness because you kind of have a goal in mind. So that's how you get there. Divide that 2 over there. So 1/2 du equals the rest of the stuff we need. It might be helpful. I'm going to rewrite the original integral. Everybody agree with me that that's the same exact thing. This is the same as 1 over x to the 6th minus x to the 4th cubed times 3x to the 5th minus 2x cubed dx. So I didn't do anything there. There's no calculus. I just wrote it differently. But now you can see, okay, what's that first thing? It's 1 over u cubed. What's that second thing? It's 1/2 du, right? So all that complicated stuff with x becomes quite simple when you put it in terms of u. All right, so it's just 1 over u cubed times the 1/2 du. You know that 1/2 is just going to go right outside the integral. And then to use the power rule, it's always advisable to write things like 1 over u cubed as just a negative exponent, because now it's the same as anything else we've done so far. It's going to be u to the negative 2 over negative 2. You can stick the expression for x back in now. I would probably clean it up first and then do that for the very last step. So that just gives you negative 1/4 u to the negative 2. And then finally, now just stick back in, okay, what was u in the first place? X to the 6th minus x to the 4th. And then with a negative exponent or a fractional exponent, so like this problem or the last one, it's always okay to leave it like this. You don't have to write it back as 1 over x to the 6 minus x to the 4 squared. I wouldn't mark it wrong, but it's an unnecessary step. Same with the last one where we got something to the 3/2. If you want to be clever, you can rewrite that as the square root of something cubed, but there's no real incentive to. You can just leave it how it is. So just don't forget the plus c. And then again, check by differentiating. It's not just a cool way to know that you're right. I really think it helps you to see that all the steps we did were just like the chain rule, kind of like the chain rule backwards. So not like a backwards chain rule, but just a way of reversing the effects of the chain rule. In the same way that, okay, every integration technique, like we get something called parts, that's a way of reversing the effects of the product rule. And it doesn't always work. It only works for specific things. So with these, you know, I know it looks weird with the dx and all that mathy stuff. Just do a bunch. The more you do, I would almost encourage you just to almost do it in your head rather than go through all this U stuff. It's almost less confusing when you just recognize, oh, they're all pretty much the same. So sometimes I'm going to have like a 1/2 or a 1/3, but then I'm always just doing like the power rule on whatever's inside of some other function. Okay, so that's the power rule, or like I call it, integration by substitution. So that's your first big integration technique.